Are y'all able to see the whiteboard? There we go. All right. So if y'all want, at the end, after I'm done going through the lecture, I can go over the assessment results as well, the policy assessment answers, which I did that in class today at the end of it. So if y'all want that, I can do that as well. But regardless, focusing on the material here, before we continue, I made a promise to y'all, and it's a promise I plan on keeping throughout the semester. And that promise was at the start of every lecture that begins a new chapter, I would give a clear motivating example for why we even do it in the first place. And with chapter 1, it was more so bringing up the idea of it, but here now we actually start getting into examples, because a lot of instructors make the mistake of only showing people how to do something instead of showing them what they can do with it. So here I've taken a bunch of snippets, not edited at all, just copy and pasted straight out of the portal. If you want to get data like this, you can go to the portal, you just log in with your credentials, go to My Tech, go to the bottom left where it says Explore Course Options. You can click on Grade Distributions, and you can see a whole lot of data like this for yourself. Now, this data, they are the letter grades from Math 3356, which is the quantitative theory of interest, widely regarded as the most difficult financial course in the mathematics department. Now, here I have pulled data from the past 3 years, fall of 2020, fall of 2019, spring of 2019, fall of 2018, and spring of 2018, in that order that appears. I didn't pull out the spring of 2020 because there was a lot of CR and NC because of the coronavirus pandemic. We don't know what those letter grades were, so therefore it's not fair to include that. You'll see here, you recall from what I showed you in chapter 1, you'd probably organize it somehow like this. Now that it's organized, we actually have to start doing stuff with it. And the two main things we can do calculations, or we can actually start visualizing it and graphing it. And the focus of this chapter is going to be graphing it. You might ask why. Here's an example that I'll show you, a very good and relevant example of why you would do it here. So you could take a look at this for a moment, and there are probably a lot of conclusions you might come up with. For example, maybe you've noticed a lot of the C's in the fall of 2018, or maybe you noticed in the spring of 2018, there were a lot of A's. Or maybe you noticed, with the exception of last semester, there were a decent amount of F's and D's. Regardless, there's a lot of things that might pop out to you at first glance, but many of these are what you might call false flags. They might at least initially look to be important, but only jumps out because there are so many people that semester to begin with. And I'm going to show you what is known as a stacked bar chart, which I'll get into the more formal definition of it as we get to the material itself. But it's basically going to be a graphical display of the percentage frequencies of these letter grades. You might say, what is the percent frequency? I'll give the formal definition as we get in the material, but a very layman definition is, what percentage of the class got an A for some instructor? What percentage of the class got a B? Or what percentage got a C? So on and so forth. So that is how I'm going to show it here. So just an example. With this one, I can tell you that P is a B. I know that's a B because I have the distribution from last semester because I taught it. In this case, in the first class, there were 52 people. We're not counting withdrawals because everyone knows some people drop the class 1 week into it. Not fair to count them for any instructor. So there were 52 people. You might say, why is 52? Well, 16 plus 26 plus 8 plus 1 plus 1, that's 52. So for example, 16 of the 52 people last semester got an A. So we would have 16 out of 52. If you wanted to, in web work, you could put it in a 16 out of 52, no big deal. But I don't want to dwell on that too much. This is an example. That comes out to 30.7%, which is 0.307. So when I show you this chart, the A's for last semester are going to be that. What we're going to do is we're going to consider the 4 most recent instructors, myself, Wong, Park, and Shirvani. We're going to take all of that data and we're going to put it into a stacked bar chart. And that is this right down here. So our horizontal axis is what percentage of the people for that instructor got an A. For example, the first one is A, B, C, D, E. No, there's no E. Now look at the A, B, C, D, or F. Now that we have it in this way, it should be very apparent the one thing that sticks out like a sore thumb. We got this one bar. Not only is it past the 40s, it's passed into the 50s. And yet notice, in class, when we had this in class, a lot of people didn't notice this at first glance, and you can't blame them. Because when we look at the data up here, that 26, that's not what stuck out. The 39 is what stuck out, those kinds of things. You can't blame them. And the reason why is because it wasn't visualized. A lot of times, to notice some of the most important trends, you have to actually visualize it. So we see all of these B's. That was me, B for Bailey. But of course, it's not the only thing. You can see we had a lot of D's. There's my cursor. We have a lot of D's for Giovanni. Go up to the A's, a lot of A's as well. You might say, okay, this is all nice and good. What's the point of this? What can I do with this? Well, when we were in person today, I asked a question. I'm sure many of you would probably raise your hand if you were in person as well. And the question I asked, obviously, you're all undergraduates. You're working on your major. You maybe have 40 hours to complete for your major, maybe another 20 hours for a minor or a double major. And the rest of it is what could be called general education curriculum or whatever fancy name they're using for it today, because every 10 years we add an extra 3 syllables to it. Who knows, maybe 10 years from now it'll be the general education of the university curriculum, maybe something fancy like that. Now, I am very sure, and when I asked this question in class, I'll ask you now, how many of you have taken at least one class for your general education that you just genuinely couldn't be brought to care about and just wanted to get your grade and get out? When I asked that question in class, I think maybe 80% of the class raised their hand. What basically happened was a few of them, their hands shot up instantly, and the rest, when they recognized there was no shame in doing so, those hands kept coming up. And that makes sense, because with a general education, the expectation is hopefully there will be a class you take that you like, but by that same logic, there's going to be a class that you can't be brought to care about. And so ideally for you, you're just taking that class to satisfy a requirement. And ideally, you want to get a good grade and not have it be all that much effort. Doing something exactly like this can help you figure out what instructor to take or what class to take. With the exception of the section from last semester, the grades were all over the place. If you're looking for just a passing grade, let's say you're looking for a passing grade. Well, you see our purple bars, there's only one grade below a C because D doesn't count. Whereas on the other hand, if you're looking for an A, you do the blue bar, or teal bar, technically speaking. And long story short, using the techniques I teach you in this chapter to visualize data like this, you can do something like I've done here for any course you want. And you can use that if you have a course you're just not interested in it, but you have to take it anyways. You can, at the very least, find an instructor or a course. Sometimes some courses, no matter who's teaching it, they're so easy, everyone passes. And so you can use something like this to make your life much easier. That's the whole point of this course, to do things to make your life easier. And in this case, you can very clearly apply it to your major. So with that, let's actually get into the material. So the first thing we have to do is make a couple of definitions. There's only 3 calculations in this entire chapter, or I guess formulas. And the first one is something we call relative frequency. Relative frequency, I put rel F, relative frequency. Our relative frequency, let me move this out of the way. Our relative frequency is given by the number of times that something occurred. So I'll just say it, being whatever it is. So for example, it might be A's, how many times the A's happened. And we divide this by our sample size. So let's use an example. Last fall, 16 people got an A, so the number of times it occurred was 16. We had a total of 52 eligible people. There were 52 people in the class after the 2 withdrawals. So our sample size is 52. So 16 out of 52. If this was a WebWork question and WebWork just said, what's the relative frequency? You could put in 16 over 52 and it would take it as an answer. Also, you can do it to 3 decimal places. We're keeping everything to 3 decimal places. It's important we be consistent so you don't have any frustrations due to rounding. So in that case, if you put 16 out of 52 in your phone's calculator, you'll get 0.30, I think like 69 or something, blah, 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 blah. We round that to the 3rd decimal place, 0.307. Likewise, we have something else, because here, this is relative frequency, but you'll notice our graph here had percent frequency. So our percent frequency, so we'll call that percent frequency, you effectively convert your decimal to a percentage, but I want to make it as crystal clear and good as possible. So that would be our relative frequency times 100.
Shoot.
And then we just add a percent sign on the end. So for example, the 0.0307 multiplied by that 100, that's 30.7, add the percent sign, 30.7%. And now with that 30.7, that's now why you see this purple bar around 30.7. Before I continue, are there any questions with regards to what I have shown you so far? All right, well then we'll keep going. Now, notice what we've done so far is for categorical data. What we have, this is all category. For example, our A's. You have an A or you don't. You can't have an A and a B at the same time unless you have an 89.4 and you're arguing with the instructor over whether or not you deserve an A. But you have an A or you don't. And just to recall, a little refresher from chapter 1, in this case, our A on its own is nominal because you have it or you don't. Whereas if we took everything and combined it together, so A through F, then it's ordinal because A is better than F. But again, this is all categorical data. So that's all we have to do for that. And that means now we can begin plotting it. There are 2 main types of visuals that we have, or graphs, with regards to categorical data. We have bar charts and pie charts. I know most of y'all have seen a pie chart before, but regardless, let me go ahead and show you. So here I have a table of soft drinks with their relative frequencies and percent frequencies. Now, a little spot check for you. You might say, hold on, what are the numbers? Well, the sample size, I'll just tell you, the sample size is equal to 50. It's up here. We have 19 Coca-Colas, 19 divided by 50, 0.38, 38%. So hopefully that makes sense given what I've shown you so far. So now we can plot this as a pie chart or a bar chart. Let's start with the bar chart because I've already shown you that. To zoom out a little bit, here we go. So right down here, we have our bar chart on the left. Here it's the absolute frequency. So, in this case, Coca-Cola, we had 19 of them. So our bar goes up to 19. Diet Coke, we had 8. So the bar goes up to 8. And then 5, 5. Our remainder, I believe, was 13. Yes, 13. So notice we can do our bar charts just in terms of the actual frequency. If we just say frequency on its own, that's the same as the count. How many of them are there? On the other hand, we can use what's known as a pie chart with our percentages. Essentially, think of it this way. Imagine you have a pizza in front of you and you want 38% of the pizza. You'll slice yourself up a percentage of that circle that's about 38% of the pizza. So in that case, that's maybe a little over a third. Likewise, the Pepsi is 26%. So imagine that as slicing up a pizza into 8 slices and taking 2 of those slices for yourself. That's the idea behind a pie chart. I'm sure y'all have seen a pie chart at some point, and I'm sure y'all have constructed them at some point before. But as you'll notice, when we were talking about the motivating example, I didn't spend all that much time on actually making it because y'all have seen these types of things before, but you haven't interpreted them many times. My focus will be on actually teaching you to interpret these things and taking all of the important things out of them. So this pie chart, we go up here, we add our 10% right there. So here we have 10 and 10. We are 16% and our 26, and our last one is 38%. Now, just as a little spot check, I'll wait for just a moment so you can think about it. What percentage of people wanted either a Pepsi or a Coca-Cola? I'll give you just a second to think about that. A little bit of a spot check. Maybe about 10 or 15 seconds, not all that much of a hard one. So here we take our 38, we add it to the 26. 64% of people wanted a Pepsi or a Coca-Cola. Now, let's suppose I asked you what percentage of people didn't want a Coca-Cola. Well, you can add up the 10 and the 10 and the 16 and the 26, or we can take a shortcut and recognize that we just take the number 1, because everyone adds up to 100%, and subtract the number of people that wanted a Coca-Cola. So 100% minus 38%, 62%. So those are the type of interpretations you do with the pie chart. And I'll give you a very clear example that comes from some of the extra practice homework as we get later in the lecture. So, but bar charts are almost always better than pie charts. And the reason why is because pie charts can only convey so much information. All they convey to you is what percentage of people wanted something. They're still useful, they're just not preferred. Because you'll notice this pie chart, it all had to be one category. The category was, what drink did you want? What happens if we have this starting data up here, and not only do we have multiple categories for letter grades, but we have multiple instructors? We can't put everything into one pie chart unless we group all of the instructors and call them Jiho Abu Talib Bailey Wang, which would be quite an interesting name. Can't do that. So we can't do a singular pie chart with this unless we group everyone into one instructor name, or if we take all the letter grades and just throw out a bunch of them. If we throw out everything but an A, then sure, we could do a pie chart, but it just doesn't tell us much of anything. So when we have multiple categories over multiple things that we collected them on, pie charts don't do us anything. You'll recall from chapter 1, we had the table of the World Trade Organization data. We had multiple countries and multiple categories. There's no doing a pie chart of that, because for a pie chart to work, we have to do a number of things over just one either category or element. Can't have multiple elements and multiple categories, or it's not a pie chart anymore. This is why we, generally speaking, prefer to use bar charts over pie charts. They give us more information, and you'll always be able to make a bar chart. Sometimes it might just be, let me scroll a little bit more. Sometimes it might just be, well, that's a histogram. A little bit, there we go, a little bit lower. There's a lot of stuff in this lecture. Sometimes it might just be 5 bars. Simple as that. On the other hand, sometimes we got a lot of bars everywhere. But no matter what, bar charts can pretty much always be made. Pie charts, it depends. So that's one thing to take note of. But the main thing we'll be focusing on is actually interpreting these. But bar charts, pie charts, those are for categorical data. We haven't talked about quantitative data. Now, an example of quantitative data are the numerical grades. These numerical grades, they can go as far out in the decimals as you want. Someone can have an 88.5436543 and go on to infinity in that many decimal places. Or someone can just be a flat 90. There's a lot of options for those, so that's going to be quantitative data. In order to plot quantitative data, we have to categorize it. For example, these letter grades, technically, all of these letter grades, they were numerical grades, but we categorized them into A, B, C, D, and F. So even though a 95 was better than a 92, we called them both an A and put them in the same category. So to plot quantitative data, we have to categorize it. Now, before I continue, are there any questions about categorical data and their related graphs and plots? Yes, bar charts and pie charts, that's correct. Bar charts and pie charts are they're for categorical data. All right. Now, to deal with the quantitative data, we have two options. We can either just throw it on the graph or we can categorize it. What I'll first show you are the two graphs where you can just immediately graph it. But keep in mind, you can only do this when the data is relatively clean. So for example, integers, if we have 1, 2, 3, 4, 5, 6, 7, 8, all the way to 100, say number of days in a month. That's quantitative data, but they're integers. And we can therefore immediately start plotting that. There are two examples of that. And let me scroll down. We have dot plots and stem and leaf. We'll start with a dot plot. With the dot plot, we just take all of our data. We plot the lowest end on the left, the highest to the right, and plot everything in between. So here, we have this table here. Now, they've already categorized it, but let's not worry about that for a moment. The point is, this is data from the IRS, from people that they've audited with regards to their tax returns. Now, people can get audited just because of some sort of administrative mistake. And generally speaking, you see those get resolved pretty quickly. Sometimes there's people whose audits last for longer. Wesley Snipes and Donald Trump might come to mind. Not trying to be political, that's just a statement of fact. But these numbers, they're in days. It's done in 20 days or 21 days or 28 days. And so we can do, we put it on a dot plot. So here, this is 10. This would be 12. So I'll put 12. That would be 13. That would be 14. These are all integers. I'll make that very clear. These are integers. That's 15. So therefore, this one is 18. This one, 23, so on and so forth. So we have a dot here at 12, which means one of our data points was 12 days long. We have another dot at 23, so one of them was 23 days long. You might say, okay, nice. Why do we have somewhere there's multiple dots all in a stack? If we have multiple dots in a stack, that means there were multiple data points that had the same value. So for example, here, we had 2 audits that took 14 days. For 18, we had 3 audits that took 18 days. And so these are what the dot plots are like. Now, again, for this course, generally speaking, I'll give you the plots and then ask you to interpret them. So an example of a question I wouldn't ask you is, here's data, make a dot plot. An example of a question I would ask you is, here's a dot plot. How many people had 18 days? Or how many people had less than 20 days? Those kinds of questions. Those are the types of questions that I'll ask you. So that's a dot plot. Another way is we can do something called a stem and a leaf plot. And again, this primarily applies for integers. So for example, here, this is a stem and leaf plot. Let me zoom to the right a little bit. For IQ levels of a random sample of people. You might ask, what's going on here? What's happening here? On the right, we have a bunch of digits. These digits represent the singles place of a multi-digit number. The left-hand side represents all the numbers before. So let me give an example. Let's suppose we had 573. That'd be quite the IQ. With stem and leaf, we take the last digit and put it on the right-hand side, and all the other digits, put them on the left-hand side. So 573, we'd have the 3 on the right-hand side and the 57 on the left-hand side. So 57 on the left and 3 on the right means we have 573 as a data point. So in this example, we have 6 on the left-hand side and 8 on the right-hand side, which means that 68 is a data point. Down here, we have 14 on the left-hand side and 1 on the right-hand side. So 141 is a data point. Now, you might say, okay, fine. But what do these 2 3s mean? Why do we have 2 3s? If we have 2 3s, here's what we have. We have a 7 and a 3. So we have 73. But we have another 3. So we have a 7 and a 3 again. This means 73 occurs twice. Same logic. We have 2 1s. So we have 81 twice. Finally, we have 3 6s, which means 106 occurs 3 times. So before I continue, does it make sense how we're constructing the stem and leaf plot? And as a note, we do it in increasing order. So the 60s came first, then the 70s, then the 80s, then the 90s, 100s, 110s, so on and so forth. Does this make sense what we've done so far? Well, given that no one has said anything to the contrary, we'll go ahead and keep going. So here, the nice thing about this is that we get a pretty decently looking distribution. You'll notice I've put rectangles around these, or well, textbook, you get the point. They put rectangles around these to give them bars. So we see we have much more in the 70s than in the 60s. We have much more in the 110s than the 130s. What this is getting at is known as a histogram. This isn't a histogram, but the idea of putting things in the classes does get to the concept of a histogram. But before I show you what a histogram looks like, we're going to get to the final calculation that you'd have to do for this chapter. And this is known as categorizing quantitative data. So we'll go up here. So I'll write categorizing quantitative data. You might say, how do we do that? Well, like with the letter grades, we put them into categories. So for example, for letter grades, for this class, we had an A is a 90 and above. We had a B is a 75 to an 89. A C is a 60 to a 74. And an F is below a 60. So that's a categorization of the grades. The grades are going to be everywhere. They're going to be all over the place, but we categorize them into letter grades. Now, generally speaking, though, in most cases, you would have our categorizations be the same length. You'll notice that this one, you'd think 90 to 100 is an A, but technically, you know, someone might go over 100. So maybe this could go up to 102. It could be 90 to 102, which would mean it's 12 long. This one is obviously 14 long. I mean, you could say 14.99999, but we'll just stick with what we have here. This one you can call 14. You can call it 15 if you want. Let's not split hairs. Keep it nice and simple. And then this one you can go all the way down to a 0. So that would be maybe 60. So notice here, they don't have the same widths. Generally speaking, it's a good idea to have everything be the same width, but obviously letter grades are the exceptions because I'm sure many people would be happy if a 30 counted as a passing grade, but then what would be the point of showing up for anything? So sometimes you have the same width, but generally speaking, we keep things the same width. And so we have something called our class width. Our class width is equal to our largest data value minus our smallest, that's an N, not an M, there we go, our smallest data value, and we divide this by the number of classes we want. So in the example of our audit times, our highest was 30, they call it 34, we can call it 34.999, blah, 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 blah. Let's just call it 35, keep it nice and easy. Our lowest was 10, so high, 35, low, 10. In this case, they wanted to have 5, so 5 classes. 35 minus 10, 25. 25 divided by 5, 5. Sure enough, these are 5 wide. 10 to 14.9999999, so on and so forth. Does it make sense how we get this class width and categorized our audit times? The denominator says Thank you. That's not as clear as it should be. Number of classes we want. So we want. There we go. Our denominator is the number of classes we want. Now, on the exams and assessments, I will tell you how many you want to have. But in practice, when you're on the job or continuing your degree, you will oftentimes get to decide that. Now, you might ask, well, then what do I pick? It's ultimately up to you. It depends on the situation. And there's so many different situations that there's not oftentimes a good rule of thumb. The closest thing you'll get to a rule of thumb is that you should try to have the class widths be either integers or something that's pretty proportional to your data. So if your data goes from 0 to 1, maybe they're 0.2 wide. Essentially, the width should be something that's relatively clean. You know, if your width is 3.4567845455 and so on and so forth, that's a bit messy. So as long as you have something that keeps it relatively clean and makes sense, that's fair game. Now, once we have our class width, in our case, we have a 12. So we have a 12, we have a 13, a 14, and a 14. Remember, we have two 14s because we have two dots. This means we have 4 data values from 10 to 14. This is why our frequency is 4. Notice now we categorized it. This is now categorical data. And now that it's categorical, we can begin plotting as we please. And here I'm going to show you the most common graph used and will display used in statistics. And that is known as a histogram. This is a histogram. This is everywhere. Even if you've seen it before, I'm going to go on it or talk about it quite a bit either way. Essentially, a histogram plots our frequency. Now, as note, that frequency, it can be the actual number, it can be percent, it can be decimal. Doesn't matter, your choice. Our horizontal axis will always be our categories. So here we had 10 to 14, then we had 15 to 19, so on and so forth. Notice that this histogram tells us something that our dot plot didn't. Our dot plot, you can see it's pretty flat. It's pretty flat, nothing all much going on there. But the moment we categorize it, we see that most of our data is located right around here with a few coming out on the tail end. And that intuitively makes sense because most of the audits that the IRS does, they just come from taxpayers making an accidental filing error. So it doesn't take too long to resolve to begin with. Only a few of them are due to genuinely nefarious things, and those generally take longer to fix. So by putting things in a histogram, it tells us something that we wouldn't have otherwise noticed beforehand. Now, if you'll notice, this histogram might look oddly familiar in terms of shape to our stem and leaf plot. The reason why is because if I take this stem and leaf plot and I rotate it to the left by 90 degrees, it looks like a histogram. Basically, a stem and leaf plot is a histogram that's rotated. So you might say, well, if that's the case, why can't I just use stem and leaf? You'll notice in this case, our stem and leaf is already categorized. You're just doing extra steps to do it. So why do the extra steps when you can just make the histogram? Don't get me wrong, stem and leaf is very useful, but the histogram gets the same thing across with a bit less effort and is a bit more pretty to visualize. You'll also remember from the very beginning when I, part of keeping my promise to y'all and showing you many of the applications, what you can do with it. You'll notice this right here. Let me zoom in a little bit. You'll notice we take this and rotate it to the left. Let me zoom out. You'll notice much of that looks oddly like a histogram because it is. If I took all of those purple bars, we'll take my purple bars. We had one around 30 for the A's. Let's do that. And then we had one for the B's up here all the way up at 50. So we'll do that. And then we had one for the C's. That's somewhere around 15, maybe here. And then we had no D's. So I'll just put a line there. And then we had the F. There's the histogram. That's the histogram for the previous semester. A bar chart is just a histogram with extra steps. That's all it is. You'll notice a lot of this boils down to a histogram because that's why everything comes down to a histogram in this course. And so that's why you'll see a lot of the focus will be on histograms. Now, no doubt, you will see in web work, I will ask you to fill out these relative frequency and percent frequency tables. I will ask you to make a couple of stem and leaf plots. And you will deal with these couple of extra things. But you'll see when we get to the assessments, you're going to see histograms everywhere. It's because they're so important. They're so useful. And as y'all have seen from the motivating example, along with the other ones, they give you so much information that you otherwise might have missed. So before we continue to some practice examples that I'll give you a little bit of time to do, are there any questions about these types of graphs for categorical data and quantitative data? I'm just undoing this so you can put it back in regular form. Okay, if there's a question, it'll pop up in chat and I'll see it. What we're going to do now, I'm going to show you a couple of practice problems, and I will give you a couple of minutes or so to work on it. So here we have this stem and leaf plot. We have one question here. I'm going to add a second question as well, and I will make it sufficiently large in terms of size. So B. There we go. So 2 questions for you to work on, give you a couple minutes to practice with. First one, here's our stem and leaf plot. What percentage of the grades are above an 80? I guess you can call that part A. And then part B, get all the data points. So I'll give you a couple of minutes till maybe 49 or 50 to work on this one. And then when we hit 49, we'll go over the answers to it. Now, if we were in person, we'd do the raising hand stuff, which we did, but obviously many of you are at home right now because we're doing this as a makeup because of technological problems. So I'll give you a couple minutes to work on it, and then we'll go over the answers. And if you have a question while you're working on this, feel free to ask and I'll be happy to answer. You can unmute or type it in chat, whatever's best for you. All right, so 49, I'll go over this one. So our first one, what percent of the scores are higher than 80? In class, most of the people correctly got it as 30%. A couple made a mistake and thought it was 20%. So here's what we know. This 84, that's 84. We have 90 and 98. We have 10 data points. So therefore, 3 out of 10, 30% or higher than an 80. Now, additionally, what are our actual data points? We have 5 and 5, that's 55. 5, 7, 57. 6, 2, 62. 6, 3, 63. 7, 1, 71. We have 7, 5, 75. We have another 5, so we have 75 again. We have 8, 4, 84. We have 9, 0, 90, and 9, 8, 98. And in this sense, it's very clear the ones that are above an 80. We got 3 out of 10, 30%. So before I move on to the next example, any questions about the one you just worked out there? All right, let's move on to our next one over here off on the right. This one we are going to work with the pie chart. Pie chart and filling out a table. You will see this pop up on your web work. So here we have 137 mutual funds, and they all have their different objectives. So 137 total. What I want you to do, spend about, I'll give you about 3 or 4 minutes because that's how much people in class needed. So I'll give you 3 or 4 minutes to fill out this table here. So you're gonna have to do 10 entries. What I recommend doing when you're working on it, you can either use your phone calculator or use a standard boring calculator, because on the assessments and the exams, you'll only be allowed to use a scientific calculator or the proctorial one. So I'll give you until, we'll do 54 to work on filling out this table. And you will see filling out tables like this in the web work. So I'll give you a few minutes to work on this one. And if you have any questions while working on it, feel free to ask. All right, give about another minute to work on it. As a reminder, what I'd recommend doing for both relative frequency and percent frequency, make sure you go out to 3 decimal places. All right. Is there anyone who needs a little bit of extra time to work on this table? All right. So with our relative frequency, all we do, we divide our entry. So in this case, our first one would be 26. We divide it by 137. We repeat this for all of them. So in web work, you can just put in 26 out of 137, and it'll take that because it converts it to a decimal for you. 26 divided by 137, there we go. So in this case, 26 out of 137 is going to be 0.1897, blah, 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 blah. So we round that to the third decimal place. The 7 bumps up the 9 to a 0, which bumps the 8 up to a 9. So in this case, we would have 0.190. We have 42 out of 137. That comes out to 0.307 because it's 0.30656. 5 kicks the 6 up to a 7. And keep going. We have 20 divided by 137. That's going to be 0.146. Our next one, we have 37 divided by 137. That's going to be 0.270. And our last one, we have 12 divided by 137. That's going to be 0.088. Now our percent frequency, we recall, we just multiply by 100 and add a percent sign. So the 0.19 multiplied by 100, that's 19. Add the percent. Easy as that. 0.307 multiplied by 100, that's 30.7. Add the percent sign, we're good to go. Now, as a note, on web work, it might or might not already give you the percent signs. Just keep an eye on that. 14.6, so we multiply by 100 to get that, add the percent sign, multiply 0.27 by 100, 27, there's our percent sign, 0.088, multiply, we get 8.8%. Are there any questions on how we fill out this table? All right. Now, I'll give you one more to work with. Here on this right-hand side, we have a pie chart of that data in percentage form. So a question I could ask you that you might see on the assessment or the web work is, based on this pie chart, what percentage of our funds are from a combination of MC and TK? Let me go a little bit to the right so you can see the labels. So in this case, we did the raise hand things in class, but obviously there's only, I guess we could use the raise hand button on Zoom, but it'd be the same idea. In this case, our MC is 14.6, our TK 8.7. Add those together, we get 23.3. Now, let's suppose I asked you what percentage of people had GI, TK, SC, or MC. You could add those all together, or we can use the 1 minus rule, where we just subtract our IL because that's the only thing we don't care about. So 100% minus 30%, that would mean 70% came from MC, SC, TK, or GI. So that's an example of something we could work on for a pie chart or, filling out a table. We'll do one more, and for this one, we're going to go back to the example we started with. So here we have this. I'll type out a few ones. You can work on these yourself. Oh, there we go. So A, who was most likely to give an A? B, who was most likely to give a B? And then how about C, who was most likely to give an F? So I'll give you about a minute to work on this one. Shouldn't take all that long. Remember, this is an interpretation one. You'll see a lot of these interpretation types of questions on the assessment, especially for histograms. I'll be giving y'all a lot of histograms and asking you to interpret them. And if you're not confident in your interpretation skills for histograms, this is one great way to help practice that. And likewise, there are multiple practice assessments in the practice assessments and exams folder for you to work with as well if you need extra practice. So I'll give you maybe a minute, so until 59, to work on these three, and then we'll go ahead and go through the answers. So our first one, again, if we were in person, I'd ask you to raise your hand, which is exactly what we did, but I'll tell you here, our first one in A, our highest bar is our blue bar. That corresponds to Shirvani. So he had the highest percentage with an A. The B, it's kind of obvious. We talked about it at the beginning. It says big pink bar. That corresponds to Bailey. So that is our B. That should be most likely to get a B. On the other hand, F, that's our green bar right here. That is Wong, so that'd be C. Now, the nice thing is you can use these types of questions. If you're looking to get an A, maybe you take it with Shirvani. If you're looking just to pass the course, maybe you take it with me. Maybe you consider yourself lucky that you're enrolled with me right now. The other hand, obviously, if you're concerned about failing, there's that to look at as well. You can very easily see how these types of interpretation questions, they not only help you understand the material, but also you can see how you can so easily use these when you're actually out there doing stuff, even if it's so simple as doing something right now. I imagine many of you will be registering for the classes in the summer and the fall. This is something you might consider. You can get all this data. It's all publicly out there and available for you. So before we continue to the last two parts of chapter 2, are there any questions about these exercises and examples that we practiced together? All right. Don't worry, there weren't many questions in class either. So we'll go the last two things. One of these here is just, this comes straight out of, let me zoom out a little bit so you can see it better. There we go. This part down here, right in here. This comes out of one of our homework things. I'm not going to assess you on this on the assessment, but it will pop up in the web work. What matters most here is, oh, where'd my mouse go? There it is. Matters most here is this part in Ogive. Now you might ask, what's a cumulative frequency distribution? If you go further into statistics courses, you'll see cumulative pop up a lot more. A cumulative distribution basically means how much of the data was equal to or less than this point. So for example, using that example we started with, the motivating example, a question I might ask is, what percentage of people got a B or lower? Or what percentage of people got a D or lower? Or what percentage of people got an A or lower? Spoiler alert, everyone, because you can't do better than an A or an A plus. Those types of things. What a cumulative does is it is the sum of how many, the count as a percentage of all the possible data of all of the values that are less than or equal to that value in question. So let's look at this Ogive. We have an example here. This is the value of meal prices at McDonald's. We can see none of them cost $0 because then that's just free food. They go to a food bank for that. We see here that 30% costed $5. And so we can see that's our 30% right here. Our horizontal axis is always our data in question, like what's the threshold. So here 5, this is our threshold. This is all in dollars. This is all in percent. So 30% is $5 or less. Now we go up to $10. 70% of our meals cost $10 or less. 90% of our meals cost $15 or less. And 100% of our meals cost $20 or less. So for example, if I didn't give you the table and I just gave you this Ogive and I asked you what percentage of meals cost less than $10, you'd say 70%. And essentially, an Ogive is the two-syllable term for what we call a cumulative distribution. If you go further into statistics, you might be majoring in it or very interested in it, you'll see a lot more about cumulative distributions. Finally, the last part, which is very important, you're going to see this on web work, you're going to see it on the assessments, it's going to come up quite a lot, and this is called skewness. So let me get to a place right down here. Very good. We have something called skew, or you can call it skewed, or maybe you want to call it skewness. Same thing either way. Skew is a way to describe our distributions or our graphs. Now, let's suppose we have a graph like this. Let me make it a bit nicer. This, we would call this symmetric. This is a symmetric distribution. Why? Because if I took it, cut it at the halfway point, brought it down, and flipped it, same thing. They're the same thing. So a symmetric distribution, if we cut a line down the middle and fold them together, they're the same thing. A skewed distribution is the opposite of symmetric. So essentially think of it as skewed equals not symmetric. A skewed distribution, it's not symmetric. So for example, let's go back up here. When I was showing you the distribution for last semester, we had something like that, and then that. Oh, that's a bit too wide. I'll make that a little bit more narrow. And that, and then that, nothing there, and then that. So if we wanted to put that on a curve, it might look something like that. That is very clearly not symmetric. If we take the part of the graph after our peak and we bring it down and we flip it, they're just not the same thing. It's not symmetric. Therefore, it is skewed. Now, there are a lot of ways to describe a skewed graph. How significantly is it skewed? In what direction is it skewed? And that's what I'm going to show you here. So we have two types of directional skews. We have right skewed. There we go. And we have left skewed. You might say, okay, which is which? Here's how you approach this. And a lot of instructors don't give this example, which in my opinion is the easiest way to figure it out. If you notice, our symmetric graph, we have two tails. One on the left, one on the right. On the other hand, in the histogram for last semester, that's not a tail. There's just no tail there. The tail is only here. We have one tail. So that's one tail. Whereas this is two-tailed. So if it helps you, if you want to write in your notes, a skew distribution only has one tail. And to figure out if it's left skewed or right skewed, the question you ask yourself is this: on what side of our peak is the tail? If it's on the right side of the peak, then it's right skewed. If it's on the left side of the peak, then it's left skewed. So going back up here, our tail is on the right side of our peak. It's to the right, so it's right skewed. On the other hand, if our distribution looked like that, our tail is on the left side, so that would be left skewed. Okay? So with skew, ask yourself this: how many tails are there? If it's two tails, symmetric, end of story. It doesn't have to be perfectly symmetric, as long as it's approximately symmetric. If there's only one tail, you have a skew. And the direction is whatever side of the peak the tail falls on. Now, another question I'd ask yourself is, how bad is the skew, i.e. how severe is it? Let's go back to our histogram over here. This is clearly a skew distribution, but if we have we draw it like that, it's skewed to the right because our tail is on the right, but it's not that severe. We basically stop right about here. It's not too far after 25. So this is what we call slightly skewed. That's a very terrible W and an E. There we go. That's slightly skewed to the left. I'm sorry, to the right. Because our tail is on the right. And notice our tail, it's a decent bit away from our peak, but it's not too far away from the peak. On the other hand, let's say we took Wesley Snipes' audit and we find it all the way off over here. Then now our distribution looks like that. This is significantly skewed. This is significantly skewed because you can see our tail is going very far away from the peak. And obviously this is skewed to the right because our tail's off on the right. Now, on the assessment, I will ask you a question like this. I will give you a histogram or a distribution, and I'll ask you, describe it. You have four options, well, technically five. Symmetric, slightly skewed left, significantly skewed left, slightly skewed right, or significantly skewed right. Usually, it'll be one of the four. Well, like I'll give you four, and it'll be one of those four. When answering this type of question, here's what I strongly recommend you do. As you recall from chapter 1, when we were talking about a type of data, the first question I posed to you is this. Instead of just figuring out flatly what the answer is, ask yourself, is it categorical or is it quantitative? Because that makes the rest of it much easier. By that same vein, it's either slightly skewed or significantly skewed if it's not symmetric, and it's either left skewed or right skewed if it's not symmetric. Well, here's what I recommend you do. Before even asking yourself, how significantly is it skewed? Or asking yourself, is it skewed at all? Ask yourself, is it left skewed or right skewed? I mean, it can be neither, in which case it's symmetric, but it'll be obvious if it's symmetric. But if it's clearly skewed, ask yourself, left or right? That's a very easy one to answer. You just look where the tail is. The tail's on the left, it's left. Tail's on the right, it's right. So answer that question first. If it asks you to describe the distribution, figure out if it's left skewed or right skewed. If you answer that correctly, even if you're not sure if it's significantly skewed or slightly skewed, at bare minimum, you have it down to a 50-50. Now you might say, hold on, Professor Bailey. Why can't I just answer whether or not it's significantly skewed or not? You can do that, but whether or not it's left or right is a very cut and dry question. You know, it's kind of like if you asked yourself, are you slightly left-handed or slightly right-handed, or significantly left-handed or significantly right-handed? I'm pretty sure if I just asked you left or right hand, you can answer that in about a second. Same logic applies here. It's easier to answer the left or right question first, so answer that first, and just like that, you'll knock out at least half of the answers. And then once you do that, ask yourself the second question. So, before we go to an example, and this is the last example before our lecture is done, are there any questions about our types of skewness? And I'll wait just a moment because I understand it might take a little bit of time to type. All right, if not, I'll give you one last one, and here we'll do it right on the fly. Let me zoom out a little bit more. Let's give us a bit of extra space. There we go. I'm going to give you 6 distributions. Let's zoom in a little bit more. One more. There we go. 6 distributions. We're going to call them A, B, C, D, E, and F. And I'm going to draw them for you. Here's our first one. Here's our second one. There's a third one. Fourth one. Fifth one. And sixth one. Look just a moment. Which one of these is the symmetric distribution? And in class, everyone raised their hands as we went through. So here I'll give you one to think about the symmetric one. And with this one, it's slightly a trick question. The answer is A. It's clearly symmetric. Some people in class, yes, exactly, Aubrey. Some people in class thought it was also F. F is technically symmetric. You're absolutely correct. But we don't call it symmetric. This, and I'm not going to give you a trick question on the assessment, but Aubrey, very, very good bringing that up. I was about to get that, but excellent on bringing that up. This is known as a bimodal distribution. This is known as a bimodal distribution. We have 2 peaks. Now, on the assessments and on web work, you're not going to see bimodal. And we're not going to talk about bimodal much, if at all, in this course. But I think it's important that I bring it up to you because you can see bimodal in the real world. Let's talk about this bimodal for just a moment. Let's suppose these were grades. And we go from, say, 40, and that's 70, and that's 100. Let's say these are grades. That's not good. We got 2 different peaks. And they're off in their own worlds. We got one peak in the 55 range and the other peak in the 80 range. That's not good. You might say, how could we possibly get a bimodal distribution on grades? The answer is cheating. If you have one group of students who are cheating and the other group who aren't, you can absolutely get a bimodal distribution like this. And this is one of the easy ways to figure out if you have some cheating going on in your class or not. So I figured I'd bring this up to show you. Now, for the rest of these questions I'm going to ask you, if there's more than one peak, it might be symmetric. In this case, it is. But let's suppose we had one like this. That's not symmetric. Because, for example, let's say we drew a line right here. We take that, we flip it. That's not symmetric. So bimodal, it could be symmetric. It might not be. On the assessments and on the WebWorks, you're not going to see much bimodal, if at all. But I figure it's important I bring it up to you because you can see how important it can be. And you will see this in the real world. It's going to pop up. But as a little shorthand, and this is more so a real life type of thing than like a class type of thing, anytime you see a bimodal distribution, that almost always means that something nefarious is going on. For example, a lot of people talk about the gender pay gap. A good way to see the gender pay gap is take men's salaries, put them on the distribution, take women's salaries. The pay gap is real because it's bimodal. Now, part of the reason why is because women often go into different professions, but there's no doubt that in many cases, even with a man and a woman taking the same job, the woman might not get paid as much. And obviously that's not fair, and that's not equal. But pretty much any time you see a bimodal distribution, there's something sneaky going on, and it's something to look out for. So it's very good, Hannah and Aubrey, that you brought that up. That's very good. Now, for the remainder, let's not worry. Let's not worry about F for the remainder. Let's now get to the ones you'll see on the exam. Now, for this one, there's two answers. Of these five, which of the two are left skewed? Doesn't matter if it's significant or slight, which one is left skewed? Give you a moment to think. Yep, that's one of them. B and C, excellent. Perfect, very good. Now, obviously, when we were in person, we had people raising their hands. So obviously, you can see how being in person makes things just as good. But that's absolutely right. Those two are left skewed. And you're both correct. And we note this is because our tails are way off to the left. Now, you might say, hold on. That's a tail. Well, we have that, and we have that. I think it's pretty reasonable to say one of those is much more of a tail than the other one. So that's another way to help you. Now, let's do the next one. There's two of them. Which two are right skewed? Give you a moment to think about that. If you want to type it in chat, you're more than welcome. You're absolutely right, D and E. Now, again, we'll notice they're not skewed to the same degree, but they're both skewed to the right. And the reason why is our tails are just flying off to the right. Now, notice, let's suppose I asked you which one of these is left skewed and significantly skewed. Even though I haven't even asked you the significantly one yet until just now, you already know if I say which one is left skewed and significantly skewed, you know it has to be one of these two because they're the only two that are left skewed. So which one of these is significantly skewed to the left? Absolutely. Yep. And so therefore C is slightly skewed to the left. Now let's say I ask you which one is significantly skewed to the right. Remember, you already know that D or E are the right skewed ones. So which one is significantly skewed to the right? Absolutely. Y'all can very clearly see now with this example how answering the direction makes things so much easier on you. So when you go up to that assessment, or for that matter, the WebWork, but especially the assessment, when it comes up on the 16th of February, which is 2 weeks from now, when you come up to that, if it's asking you, describe the graph. Obviously, if it's symmetric, there you go, end of story. If it's not, here's a question you should ask yourself. Left or right? Don't even worry about the significance. Just ask yourself left or right. You get that right, just like that, y'all saw it makes it so much easier on you. Now, one final thought, and this is the very last thing we have. Let's suppose you have a graph that looks like this. It kind of looks like a traffic cone or a banana peel. That one's still symmetric. It is still symmetric. It's not skewed. It's condensed. We call this condensed. Here's another one. Let's say you have one like this. You can have that. That's possible. The very formal name of that distribution is the, I think it's called the delta distribution. But long story short, it's a very goofy looking distribution. I mean, there's so many ways you can describe it. Like a mountain all off on its own, a very steep mountain. This one, it's still symmetric. It's not skewed. I mean, you could call it skewed to the middle if you want, but every symmetric distribution is technically skewed to the middle. So if you see a goofy looking graph like this and you're not sure how to describe it, it's almost certainly going to be symmetric. Here's why. We take it, let's flip it. Look at that. Pretty much the same thing. And again, I would note with symmetric, it doesn't have to be perfectly symmetric. As long as they're pretty, like, when I had that here, you'll notice they're not perfectly the same, but they're pretty much the same. They're approximately the same. Now, when it comes to the assessments, I'm not going to split hairs. I'm not going to give you a graph like this and ask you if that's significantly skewed or slightly skewed, because that one, I'd call that moderately skewed, but we're not dealing with that. It's slightly or significantly. On all the assessments, it will be, at least in hindsight, it'll be crystal clear which one it is. I'm not going to split hairs. If we're doing trick questions, it will be during the lectures to help you learn, like with the bimodal one. But regardless, that is actually all the material that there is for this chapter 2 lecture, and this is an hour and 10 minutes, which is exactly how long it was in class. So if you have any questions, you're more than welcome